so now let's see how we can actually use this theorem in practice. So this would be the first solution that we're going to discuss is a Monte Carlo policy gradient based approach. So this is a sample-based gradient estimation where we still use the same derivation that we saw previously, that is that the gradient in J is proportional to mu of S, the probability, the normalized probability of visiting any of the states S, multiplied by the summation of actions that we can take at state S, of all of the Q values multiplied by the gradient in our policy for the specific action that we are summing over. Now we can rewrite this expression again instead of computing the distribution over the normalized distribution of visiting each one of the states, we can actually apply our specific policy, the policy that we're using, and well, we're going to visit some states and we assume that we're visiting the states from the same distribution of state visitations, right? But we don't actually know this distribution. Instead, we're going to sample trajectories and actually visited some states. So we're using the definition of an expected value and we remove this probability and we'll just use the expectation over the remaining value from states that we actually sample in the environment. So we can now use this gradient estimation for policy gradient steps by just sampling trajectories from our environment, right? But there is another issue that we need to address here, which is the following problem. If we're going to use this policy gradient estimation, this gradient in J estimation, we still need to compute the expected Q value over all of the possible actions in a given state at any time step, St. And this might be a problem because at state St, after we finish at a specific trajectory, again this is a Monte Carlo approach, we only took a specific action. We took one action and followed the trajectory, and we have a pretty good estimation of the Q value for that action, the action that we actually took. What is that estimation, by the way? Just the sum of rewards that we've seen after taking that action. But we don't, unless we do some clever tricks, we don't have an estimation for all of the other Q values, right? So we actually would like to avoid relying on the Q values for those actions that we didn't take. So we can't assume to have a good estimation of the Q values for those actions that we didn't sample. So the question is, can we avoid these approximations? What do you think?
Yes.
Yes, how? So again, using some, usually when we want to get rid of the summation of probabilities, what do? The expected value trick,
yes.
Right? We do a sampling based trick where we sample one of the actions from the same distribution, and that's fine, but in order to do that, to use this expected value trick, we need somehow to multiply these values by some kind of probability, right? And then the probability of taking the specific action. And then we can use the expected, can just sample a single trajectory from the same distribution over the actions, and we'll say that this single sample comes from the same distribution and it's unbiased. It's an unbiased approximation of this value.
So we already did use the expectation trick to remove
the state distribution,
yes.
Right?
So we'll be using it again
to remove the extra action distribution. Yes, we're using a lot of sample-based tricks. We're transferring a lot of expected values into sample-based approximation, and one might say not very good sample-based approximation because we're using a single sample. So I agree, it sounds a bit a bit not hand wavy, but very noisy. But this is why, for reinforcement learning, we repeat this process many times. Actually, sometimes in complex domain, we do it millions of times, millions of interactions. And eventually, our gradients point us in the right direction. But by the way, as you already observed in your home assignment so far, you see that the learning using reinforcement learning, where am I? Is very noisy, right? So all of these gradients, also in our value estimations, same goes to the policy gradients, are very noisy, and the performance hopefully shows a learning trend over time, but the learning trend is very noisy. Okay, so indeed, let's use the trick of an expected value of a single sample. So we'll have to multiply these values by some probability of taking that action, specific action under the policy that we're using. So yes, we can avoid this approximation using the expected value trick. This is exactly what's been done in the reinforced algorithm from 1992. I know that it's a very old algorithm, but it is still the basis of a lot of state-of-the-art algorithms, right? They extend it in some sense, but it is the basis of many of the state-of-the-art algorithms. So we'll have as before, we have the gradient. We'll do gradient descent step using the policy gradient theorem, the one that we derived so far, by using the expected state over the policy, expected state that we're going to visit at any time step, time step t for instance, under a specific policy. But now we need to try and avoid this term. For this term, the summation over all possible actions, we do know we can easily compute the gradient in our policy for any action. That's not a problem. This is a problem. We don't want to compute the Q or to rely on some Q estimation for action other than the action that we actually chose under the specific policy. So, as we said, we'll just multiply that by the probability of taking any action under our specific policy. We'll still use the summation. We'll divide by that value. Just multiply and divide by the same value, but now we'll be able to use the expectation trick. Right? Indeed, this is what we're going to do. We'll multiply by the probability of taking a specific action, any of the action, right? Sum over all of the actions. And then we multiply by the probability of taking the specific action. We'll divide by the same value, so I didn't change anything here, right? It's the same expression exactly. We multiply and divide it by the same value. But now we have a nice structure here that represents an expected value. Not this expected, right? So this expected value still remains, but we now have a new expected value inside the rectangle parenthesis here, because we have a summation of value of the probability of drawing this value times some expression that relies on that value. Great. So this is exactly the expected value of this term under this distribution of drawing the action. Right? I provide the definition of an expected value here, as we've seen many times before, a trick we commonly use. And now I just replace that by the expected value. I should have written here. So this is also expectation over drawing an action. Should be here, an expectation over drawing a specific action AT under policy pi. And this expectation is for the drawing state ST under policy pi. Okay, so I should have another expectation here for drawing. So this expectation is for drawing ST. Oh, go away. ST, need to do it without touching the screen. ST. Under this policy, and then we need another expectation for drawing AT under the specific policy from the distribution defined by our policy over our current state. and another parenthesis over all of this, right? Make sense? I'm sorry if it's a bit confusing. I mean, I know it's a bit confusing, but hopefully it makes sense for you guys. And of course, if not, feel free to ask questions in our discussion board. I'm happy to. I'm always available there and to answer questions. Okay, so next we're going to say that our Q estimation for a specific state and action pair that we sampled by following our policy, we can use a value approximation to do this. And then, by the way, if you use value approximation to define the gradient, then it will be an actor-critic algorithm. But let's push that later. We'll discuss this later. For now, we have a very easy sample-based approach, Monte Carlo-based approach for approximating Q for a given scene state and action pair, a state and action pair that we saw in our current trajectory. And this is specifically the G, capital G value, right? Capital G value is a single sample of the Q value drawn from the real environment, so it's an unbiased estimation of the Q value. And that's it. We have a practical way to approximate the policy gradient, which is the return that we saw after a specific time step times the gradient in the policy for taking the specific action that we took at the specific state over the probability of taking that specific action at that specific state. I know it might be a bit non-intuitive, but if you follow the math is correct so far, right? So the math tells us that this is the case. I'll try to also tell you, explain why this is also an intuitive result, right? It makes sense that this is the way that we want to update our policy here. But for now, we just did the math, and the math told us that this is the correct way to update our policy. And indeed, we can just use this gradient estimation and plug it into our policy gradient steps. So the stochastic gradient is not descent, stochastic gradient ascend in this case, right? And indeed, this is the full update rule that is used in the reinforced algorithm.